Hey, thanks, Andy. Got my camera on there, so nice to meet everybody virtually here. Thanks for taking the time out of your day. So I'm excited to present on this topic. It's kind of near and dear to my heart with some of my background you'll see through here. But we'll talk about how we can expedite our process from concept to manufacture by maximizing wave tools for collaboration, accuracy, and speed. And just a little bit about Saratech. So Saratech is a platinum level software partner with Siemens software. And you can partner with us to engineer and manufacture your complex products with better efficiency, reduce costs, and ultimately deliver better products faster. So we provide engineering and products development services. We provide direct product development improvement services. We also support software sales, implementation, and training. And then we actually also have some manufacturing capabilities with some really good 3D printing solutions. So if we can help you in any of those areas, please don't hesitate to reach out. And a little background on myself. I'm an industrial designer by schooling. I've spent most of my career in recreational marine and electric vehicles. You can see marine electric propulsion with a couple of different companies, whole form development with a partner in running Star CCM Plus. Got a lot of background in resin infusion and advanced composites, and then also with that electric world, some wheeled electric propulsion projects as well. But as a designer, I'm very interested in design thinking and very much an advocate of process to make your development into a viable product better and smoother and faster. Today's agenda, we're going to go through a case study for HCB Yachts, where I have formerly worked before coming on here at Saratech. And we're going to talk about challenge of a launch date. And if you know recreational marine, you'll know that launch dates are always a challenge, along with a lot of other industries. We'll talk about traditional processes with hand patterning and look at a solution to that challenging launch date in terms of a reference model and digital patterning. We'll talk about how we were able to take a baseline process and make it faster and the lessons we learned from that effort to expedite our process. And then we'll look at a couple alternate tasks. There's a pretty good use case in a complex hinge and a complex seat design that we had great success with these methodologies. And then ultimately we'll look at how that digital twin in all of these instances was successful. So jumping right into it, HCB Center Console Yachts is a premier manufacturer of ultra premium center console yachts. The company's got a 53-year history. Their largest boat is the 65 Estrella, which remains the world's largest center console offshore yacht. HCB's kind of claim to fame is unlimited customization. They let customers really do whatever they want, and their models are really fully loaded. Major design changes, all the options. Core models are a 39-foot, 42-foot, a 48, a 53, 60 or a 56-footer, and a 65-footer. And I guess one of the big sales pitches would be best in ride, best in class ride, and durability. So, as I mentioned, the challenge here is launch date. We've got two entirely new models that we introduced 8 months apart. First one being the 48 Campion at the Miami International Boat Show in February, and then followed by the 56-foot in October at the Fort Lauderdale International Boat Show. So, these are ground up, no reused componentry, pretty tight schedule. And what we're going to focus on today, it may seem unexciting at first, but it's a great case study. We're going to focus on upholstery. And I don't know if anyone out there is an upholstery guru, but the bottom line is it's actually got a lot more bits and pieces than you'd expect. So it makes a pretty good case study for this methodology. So with upholstery, we would look at in the recreational marine industry, traditional process, and this is still going on in a lot of builders today, hand patterning. And if we have a show deadline, hand patterning, I was able to identify really, really early was just not going to make the deadline. And that's because it's very much a sequential product flow or development flow. You really can't do very many things in parallel. So from the time that you make your plugs, you make your molds, you make your fiberglass lamination, you've got to pattern the substrates. Well, traditionally they're patterning that by hand. Literally, they still do this today. They're going in the boat with cardboard and patterning by hand. Well, you can't pattern your foam until you've got your substrates patterned, and then really you probably want to cut them up, digitize them and cut them on the CNC. Then you really can't pattern your vinyl by hand until you've got foam and substrate to sit there and do the hand work, as you're seeing on some of these images, to pattern. And then, the trim holes in the boat, how are you going to mount these things in the boat? Again, they traditionally hang the substrates in the boat and they hand trace this with craftsmen. And great craftsmen can do a great job of this. But it is a sequential process that's very reliant on hand skills. So I think most of us on the call are probably past this, process and more digital, but it just reinforces the fact, at the end of this, what you always come to in hand patterning is that there's going to be misalignments. You're going to need to tear stuff down and rebuild it. You're going to be drilling new holes in the fiberglass, which ultimately ends up with gel coat repair. So, your schedule just gets drug out to get show ready. Conversely here, we can digitally pattern with our tools, and as a spoiler, it is faster. And the reason it's faster really is from the day, so plugs are being milled, okay? Like that's occurring, but we've got digital plugs, we've got digital files for those surfaces to go to mill. We can immediately start in parallel substrate patterning, foam patterning, vinyl patterning, and trim holes, all in parallel development with multiple engineers. And we'll talk about how we're going to utilize Wave to accomplish that. And what that ultimately rolls out into is then we can go directly into CNC programming. We can go directly into sewing and installing on the boat. And time and time again, we prove that we can come out of the digital world with digital trim patterns, with all the digital CNC files, and we can install it first go in a production workflow, and we don't have every now and then you make mistakes, right? But generally speaking, there's no misalignments, which means no gel coat repair. We take those entirely out of the process. Now, I'm going to ask you guys, out of that process, what was left out of the schedule? Feel free to drop it into the questions if you want to guess here. You guys, at Realize Live, they all got it like pretty quick. Anyone got an idea what I left out of that schedule? I won't kill a whole lot of time here, but what was left out of the schedule is not a manufacturing step, but it is design, right? So, okay, great. Like we're talking about how we manufacture all these details, but how did we get to the fundamental design of where we're headed? And again, this is a great part about this process with wave linking that we'll demonstrate. How can we quickly develop and approve the aesthetic and functional direction? So here you have the interior pieces for the 48, the first of the two models we did. How did we arrive at this aesthetic direction? This is a ground up development. There was no concept or baseline to follow. We were just given the directive, do it better. So obviously you've got to concept this, right? And so the solution that I'm proposing today has worked well for me in a lot of scenarios, but I'm going to call this a reference model. The reference model, we need a concept approval ASAP, right? So I need to be able to present this to upper management and different stakeholders and get refinement done quickly, finally get buy-off on the design, and then commit to the real engineering effort. So who here would believe that design is divine inspiration? Just, hey, I'm a designer, I do great. I'm first one to tell you it is not. Design is an iterative progression. And so what we need for successful, product design is quick iterations represented with realism so we can get definitive feedback and concept approval. And so here I didn't capture in my process, right, all the different stages, but concept number 1, concept number 2, I've added these details. Concept number 3, I've adjusted some things. But the bottom line is I'm modeling essentially in a reference model, which is a single part file with multiple bodies in it, multi-body single part file where I can quickly iterate these concepts directly, linked to the production surfaces, right? So we're already milling these plugs. We've already sent this out to mill. I've got these production surfaces. I can model directly in there, quick and easy. And I can do this really fast. And moreover, once I've got that foundation, I can make changes really fast, right? So day after day, we can go in for design reviews, finally get buy-in, and we haven't invested a huge engineering effort. So then how are we now going to distribute that, right? Because this doesn't get me anywhere. There's no detail here. You can't directly send this to the mill and make it. So how are we going to get there? Well, we're going to wavelink and we're going to collaborate at this point. So this is the master model concept, and this is a big part of, the Siemens workflow that is so superior. We can split the workload and batch processes out. We can, the first stage here, now that I've got an idea of where I'm headed with this, now I can put an engineer on, Excel or Team Center developing part numbers. In the case of HCB, we did use Excel. It worked great. But you can actually see what your part count is, what your assembly count is, right? At the beginning of the design, we had no idea. But now we've got the concept. We know where we're headed. I can grab all these part numbers, right? And I can assign all these, and I can build my structure quick and easy. And now I'm ready to collaborate. We can basically go into our attributes where we can do, set up the assembly models and apply the attributes, like ignoring, certain things from the parts list, copy pasting attributes. People will say, well, attributes take so much time to populate. Well, not really when you're organized, right? Because you've got a bunch of similar products, and you can copy paste attributes across a whole, 50 of them at a time. And so it becomes very quick and easy to populate your attributes. And then we've got another guy over here focusing on substrates, and we've got other people here focusing on detailing of those substrates, another person focusing on foam, another person focusing on vinyl, and another person, focusing on part drawings. And because this is broken into different sub-assemblies, this can all be happening concurrently with multiple engineers. And assembly drawings, another one here that you can tack on at the end as well. And so what I'd like to talk about with wavelinking is there's kind of two ways that I would say you could do this. Wavelinking can be done in what I'm going to call the part context. And so in the part context, basically what you're doing, I think, is what I'm going to say is we're going to create a non-physical assembly. We're going to insert the reference part into the work part, right? So I've got this reference model, right, my concept model. I'm going to insert it into part 1, part 2, and part 3. And then I'm going to wavelink the required geometry in the context of the individual parts. And then what I'm going to do is I'm going to define that reference part as what I'm going to call non-physical by 3 actions. I'm going to exclude it from the model reference set so it's never visible. I'm going to change the reference set to empty so that it's not loaded, unless we need to return to it for updated geometry. And I'm going to set the plist ignore attributes so that it doesn't pop up on my plist. And I can do this in the part level. I don't have to redo it every time everywhere it's used. Now the pros with this direction in terms of part context is that the reference model is available to open directly. It's very easy to see. If I'm in part 2, I know immediately where that geometry came from, and I can just open it. And I can go edit that geometry, and immediately part 2 is going to update. The other pro is that the link is not dependent on any other assembly, right? So the wavelink is in the context of the part. It's not in the context of the assembly. So it doesn't matter what I'm doing with my assembly structure now or in the future, the wavelink will stay alive. Now the con, it's a little bit slower process because there's more mouse clicks because you have to do this over and over and over, right? So every time you make a new part, you're going to have to do these, the 2 steps, right? The plist ignore can be done on the part level, but you'll have to do these 2 steps after you wavelinked. Now the other way that we can do wavelinking, and this is what's really, really cool about NX, you can wavelink up or down the assembly tree at any level you want. And it's all just as robust as any other direction, right? So you're not sacrificing in terms of stability of your files or performance or anything like that. but we can wavelength in the assembly context. And so here, what we would do, we've got an assembly, we'll put that reference model at that assembly level and also on the same level as our individual parts. And then what we can do here is we can make each part the work part and wavelength the required geometry. So if I want geometry from reference model into part A, I just double click and make part A the work part. And then I can wavelength the geometry I want from here into part A. And then I can go open part A in its own window if I want to, and I can work on that geometry to grow it. Now the pros of this, that it's faster. There's no non-physical steps, right? Like you're putting it here one time, you're excluding it from the model reference set, but then in each of these instances, the wavelength geometry doesn't require any other action, to be accurate to the physical production. The con of this direction, the link geometry in the child parts is dependent on the assembly, right? So this assembly has to be alive in the same order or you'll break the links. And then determining the geometry source from the child parts requires viewing the information dialog. So if you're in part A, right, and you haven't opened this assembly, this part isn't loaded. What you would need to do is right click on the wavelength geometry and look at the information dialog, and then you can determine from that reference model was the source, and then you can go open the reference model, make your edits, and then that geometry would roll out. It just takes a little more effort to get to the source of the geometry. And yeah, like I say, it's editing the geometry requires locating and opening a named file instead of just double clicking it in the tree. Now, let's talk about those waved workflows in a real world situation. So we can go up or down the assembly tree. And you might ask, why would you want to go up or down the assembly tree? Like, what would be the use cases? So recreational boats is a great opportunity to describe that. We would typically, in developing a boat, we would start with a hull. That's going to be our foundation, our running surface, right? That's really, that's the platform that everything else is built on. And so we might design what we would call the hull molded part. So this is a hull that is just the surfaces. They haven't been trimmed yet. It's what, it's what everything's going to run on. And then what we would do in terms of making the assembly realistic is we would go down, and within hull molded, we would go down the assembly tree. We would put the hull mold in the hull molded part, right? So this is the tool that we would make this fiberglass part from. He lives here as a child in that assembly. We're wavelengthing that geometry into the hull mold. And then we're also going to go wavelength this geometry up the tree into a hull trimmed. Okay, and this is really a critical piece that I think a lot of industries can use, and definitely composites. You have a molded geometry and then you have a trimmed geometry, right? You're gonna drill some holes in this, you're gonna saw some stuff to it. So by separating this assembly level, we avoid circular relationship, okay? Because I can reuse the whole molded geometry over and over and over. And in that same assembly, I can have, the whole trimmed, and I don't have a circular relationship because I'm not wavelengthing the whole trimmed geometry. I'm wavelengthing the whole molded geometry over and over and over. So separating this by an assembly level is really critical. And it also just gives you that opportunity to say, okay, I've got a molded part. I'm going to trim it in 5 different, ways for 5 different products. So now I can have a different part number for each different trim. They both contain the same molded part. They both contain the same mold number. And then we'll come out of the whole trimmed and we'll go down here and we can develop whole trim patterns, which I'll show you. You can flatten the surface and you can develop these patterns that, you can plot and tape up in the mold for trimming. And then what we'll also do with whole molded, we'll go over here and we'll reuse that geometry, and we're going to go reuse it in the deck molded, right? Because the shear line, we would call it, where the rub rail, the protective rub rail, where the shoebox fit of the hull and the deck come together, well, we call that the shear line. Well, fundamentally, the shear line from the hull is going to transfer the deck. And so I'm going to call this a non-physical assembly. Whole molded doesn't actually live in the deck, but I'm going to put it in there so that I can wavelength that geometry up to the molded deck. I can then wavelink, the finished molded deck geometry down to the deck mold. I can wavelink it up to a trimmed deck or multiple trimmed decks, and then I can wavelink that down to deck trim pattern. So the flexibility to go up and down the tree really allows us to get this realistic assembly that is very robust and avoids circular relationships. So like I'm saying, I would call this a non-physical assembly, where we create the assembly, we wavelength the geometry we need, and then we do those 3 steps. We exclude the model reference set, change the reference set to empty, and ignore the P list on the component attributes. So that whole mold lives here, but it's not actually part of the bill of material or physical assembly. And then this will go over here in the boat assembly. We have a hull assembly and a deck assembly in most simplified terms, and inside those we have hull trimmed and we have deck trimmed. So, that may be familiar to you or unfamiliar, but point is wavelinking up and down the tree. The next thing then I would talk about, okay, so another benefit of doing this reference model kind of workflow is that we can look at a time study. So how many hours is this going to require? How are we going to get it done on schedule? I can do a small isolated project and I can evaluate my schedule with that. I then know how many, I know per cushion how many hours are involved. I can extrapolate that and I can plan for the full load of the larger project. And if we look at that in terms of, our case study with HCB Yachts, in this particular, workflow, people will say attributes, part numbers, fasteners, this stuff takes too long. You don't have time. Don't do that stuff. Well, okay, let's look at the time. It's 27% in concept and design reviews in a reference model. We only have 4% for part numbers, 3% for setting up assembly models and attributes, 2% for, 4, 7, 9% of your time is actually developing that, formal structure. And then 31% of your time is detailing the parts, getting them ready to go to the mill. And then only 6% of your time is finalizing the models, adding fasteners, making movable parts movable, right? That's a pretty negligible amount. But then we jump back up here, manufacturing drawings and exploded assembly drawings take some time. And then trim patterns, look, it's 4% of your process. It's worth doing. You can't do it faster than that by hand. But here we're looking at a process where in the 48, there are 43 cushions, which involve 653 parts and assemblies and 403 total vinyl pieces. That's 1,056 part numbers, which is why upholstery is a good example of this. This is a big chunk of work that can be divided up. So in the case of HCB, we did one boat. Now we got to do it faster. We're making a bigger version with the same concept. So what can we do to get this done faster? Well, the concept goes faster because we're just copying geometry, right? So a lot of what I could do is a reference model. I can just do a save as of that reference model, and I can go in and use synchronous modeling, etc., to just modify, right? So I wasn't remodeling from scratch the concept, so that saves a lot of time. Detailing the parts. So now and this is what we'll walk through. I chose to, because I, had a smaller team for the second project, I chose to just put more detail into the reference model. And I'll show you what that looks like. I cut roughly 5% of my time out, but we'll look at the pros and cons of what that got me. And then also here we looked at, saving time on manufacturing drawings. Well, for substrates and foam, we were able to just program directly from the 3D with no drawing support. For vinyl and the bill of material, we still needed the output, but so we cut 13% down to 6 by just using basically model-based definition. Here's a 3D model, mill it. You don't need a drawing. Same thing with exploded assembly drawings. Instead of spending 11% of our time there, we spent 0% of our time, and we utilized JT to go for, basically the production floor had the 3D model, and that's how they knew how to put it together. So 35% less time. So lessons learned out of that. So like I say, in the 48, you can see there is these are just solid bodies. There's no breakout of substrate foam vinyl. There's no detailing of fastener engagement or anything like that, right? That is the fastest reference model. You can see here the reference sets I have there. They're basically just the different areas of the boat. On the 56, I went ahead and broke it down into foam, vinyl, and substrates, and detailed some of the substrate level detailing. And so what that does is it allows me to kind of consolidate operations, right? Instead of wavelinking this body into 3 different parts and cutting it in 3 different, assemblies, I can now just cut it one time, and I can wavelength specifically just the body I want. So it's faster, but here's what we learned. The idea of consolidating sketches here really doesn't save you a whole lot of time. The model does get heavy, right? So now this is a pretty long feature tree to get all of these different reference sets and all these different features in one. So the model gets a little bit slow, and if you want to go up the tree to make a change, it doesn't happen as fast as you may want it to, and it occasionally, feature trees break when you do, mass updates. So with revisions, what we found is it's really best if you take this approach to just apply synchronous modeling or other tools at the end of the feature tree, rather than rolling up to a fundamental change that's going to break a bunch of stuff. Just leave it alone and go to the bottom of the tree and add features. It tends to be faster in some cases. And you organize the model with reference sets. But the biggest consideration here is that there's less master model benefit, right? Now I have one guy working in one file versus a master model scenario where this guy is reused in a bunch of different files and I can have a bunch of different people working on it. So, the question is, is that worth it to save 5%? So, digital twin, I kind of touched on this. This is our feedback from production floor at HCB. I mean, these are East Tennessee boat builders. They are hand skilled. They are not computer people. So the argument would be, hey, they can't use a computer. Well, this is their direct quotes. Man, this is great. Can we get this on all the other models? And that was legitimately the question. Even on the existing models, they're like, man, this helps me so much and it is so easy to use. They didn't have any trouble learning how to use JT to go and navigate that model with a space mouse. It took them a minute to get used to a space mouse, but and I've seen this at a couple of places. And the bottom line is, production people want to do their job well, but doing their job well requires clear instruction, and that takes a lot of time to develop in drawings. When you just give them the 3D model with a JT, it's all there and it's all visual, and so that really helps. So, paid way to do this, get everybody on Team Center. If you can't get that to fly past, your budgets, you can get JT to go and just, put those JTs in a production server location. Now, what I'll do is I'll talk about a alternate task here that we did of a hinge. Let's see here, I got to get these videos to load. Come on. We did a little run through and these videos, there we go. So this is a scenario where we needed a complex motion of this hinge for a bass boat. We started a bass boat company called Icon, which look it up, iconboats.com. It's pretty great. But with the dash, we wanted, this opening hatch. This boat's going to be running 70 mile an hour in, downpour rain, and it needs to be bone dry. So you can see there's a big gutter. And this RTM part on the top goes into the gutter and then needs to lift up out. Well, I don't know a mathematical way to develop this kind of multi-link hinge. Maybe you guys do. Not found it yet. So I do guess and check with sketches, right? So I can do sketch parts and just get that geometry dialed by copying sketches and just moving the pivot points and get the geometry optimized. And then I can wavelength that sketch over to parts and I can build that movable assembly. And on the very first article, this worked exactly as intended, right? So I don't know, another way to really achieve that kind of complex motion, and definitely as fast as you can by just, having sketch geometry and then wavelinking that. Another example here is the suspension seat for that bass boat. So we did a custom suspension in a resin infused fiberglass hard shell, and this was just a goal, right? This was on paper, we want a resin infused hard shell and we want a custom suspension. How do you achieve that? And we want it super lightweight. It has to be a lightweight seat. And so it was really kind of faster and easier to kind of conceptualize this in a multi-body single part. It's kind of an isolated project. One guy working on it. Just get this figured out, right? As fast and easy. and then you know where you're headed with your assembly. Then you can build out that assembly tree, wavelength the parts, detail what you need to detail, and that makes a really good workflow. And ultimately here, we brag on digital twin success, not just in terms of these projects, but just in general. We would say icon brand launch. So Ed Miller is a great friend of mine in the boat industry. He's been around a long time, done a lot of stuff by hand, and he is one of the guys that, well, that won't work, and here's why. And he's not wrong. He came out at the end of this build and he said, this was the best first article I've ever been a part of. Everything fit. We weren't trying to figure it out on the first article production floor. And the reason is that high level detailing is efficiently achieved in NXCAD with team centered data management. The workload is distributed, so we can have multiple people contributing collaboratively and simultaneously to catch their mistakes and improve ideas. Issues are easily identified and efficiently resolved in the digital twin. Way faster to change a fiberglass surface in the digital model than it is once you've milled a plug and made a mold and made a fiberglass part. Now you got to make a change. Ultimately this rolls into, I'm gonna call it 10 times cost savings or time savings, and a huge cost savings as compared to resolving mistakes on physical builds. And this was what Ed was getting at. Every hole we drilled in this thing was drilled off a trim pattern. The parts bolted in, they fit, they didn't interfere. There were literally no holes on this entire ground up boat that had to be repositioned. We just built it from day one, and it was essentially production intent and no changes. So with that, I'll leave it to your questions.
All right. Thanks, Matt. I think that's all the questions we have, so you can move on to the next slide. Again, if you have additional questions, please feel free to reach out to us at any time, and we'll make sure to be in touch with you and answer those questions. Thank you very much, and we hope to see you in the near future on the next CES. Thank you, Matt.
Thanks, guys. See you.